Right. So the graph here shows you the binding energy, average binding energy per nucleon. Okay. For various nuclei. On the x-axis, you have the mass number of nucleons in the nucleus. That is nothing but the mass number. A. So we see that nuclei which have a mass number less than 30, okay, or nuclei which have mass number more than 170, less than 30 and more than 170, have binding energy per nucleon less than 8 mega electron volt. And if binding energy per nucleon is less than 8, they are unstable. So these small nuclei are unstable, and these heavy nuclei are also unstable in nature. Okay. So any system naturally will tend to attain stability. Now, if you consider a heavy nucleus, okay, for example, let's consider some nucleus whose mass number is 240. This is a very common example taken in books. Now, 240 is greater than 170, so this is an unstable nucleus because its binding energy per nucleon will be less than 8. Now, for 240, if you see, it is approximately 7.5. Per nucleon, the binding energy is 7.5. Means to remove one nucleon from the nucleus, you will have to supply 7.5 mega electron volts. To remove all nucleons also, you can tell how much energy is to be supplied. So let's say this nucleus with mass number 240 has binding energy per nucleon of 7.5 mega electron volts. Okay. Now, if this nucleus splits into two smaller nuclei, okay, maybe identical smaller nuclei or non-identical also. Suppose it splits into two nuclei whose mass numbers are 120 and 120. Okay, two identical nuclei. Now, mass number 120 corresponds to stable nucleus. Okay, you can see here mass number 120 has an average binding energy per nucleon of about 8.5. Okay, anything greater than 8 is stable. So Y has a binding energy per nucleon of, let's say, 8.5 mega electron volts. So if X240 splits into two nuclei of Y120, it's like unstable nucleus converting into stable nuclei. Unstable means high energy, stable means low energy. So a high energy nucleus splits into two or more low energy nuclei. Okay, they are called the daughter nuclei or the fragments. And the energy difference is released in the form of heat. That is what we call as nuclear energy. And heat is nothing but kinetic energy of molecules or fragments. Okay, actually, when a heavy nucleus splits into two smaller nuclei and attains stability, the energy difference appears as the kinetic energy of the daughter nuclei. Okay, these two nuclear fragments that are formed will be moving with significantly large kinetic energy. Okay, that is what we say is the energy released in the reaction. It's also called the Q value of a reaction, nuclear reaction. Okay, now let's see how to calculate these Q values. So consider this reaction itself. Let's say X240 splits into two daughter nuclei of Y120. 240 is unstable, 120 is stable. 240 has a binding energy per nucleon of 7.5 mega electron volts. 120 has a binding energy per nucleon of 8.5 mega electron volts. Now you have to find out how much energy is released in this process. Can any of you tell me an idea how to do this? Unstable is converting to stable, so energy will be released. How to calculate the energy released? Generally, how do you find out energy released in reaction? Energy of the reactants minus energy of the products. Reactant should be high energy, product should be low energy. Then it becomes an exothermic reaction. The difference is released. Now this 7.5 mega electron volt is binding energy per nucleon. Now X has 240 nucleons. So the total binding energy of X is 240 into 7.5. How much is 240 into 7.5? 1800 mega electron volts is the binding energy of one nucleus of X. Okay. Next, binding energy of Y. Y has 120 nucleons and binding energy per nucleon is 8.5 mega electron volts. So 120 into 8.5, that is 1020 mega electron volts. For each nucleus of Y, the binding energy is 1020 mega electron volts. Now, how many nuclei of Y are formed? Two nuclei are formed. So total binding energy of the products is 1020 becomes 2040 mega electron volts. So binding energy of reactants is 1800 mega electron volts, whereas binding energy of products is 2040. Does that mean products are having more energy than the reactants? Is this an endothermic reaction? What do you think? Binding energy of products is more than binding energy of reactants. Does that mean this is an endothermic reaction? You can answer this if you know the meaning of, if you understand the meaning of binding energy properly. Binding energy is the energy you need to supply to free the nucleons. It's not the energy that the nucleus already has. Okay. So you can say that the energy which the nucleus has is negative of the binding energy. Okay. I would like to explain something analogous here. You consider gravitation, for example. Okay. Suppose there is gravitation you can take, you can consider atom also. Okay. We discussed atoms recently. So let's consider an atom. Suppose this is the nucleus and an electron revolves around the nucleus. Fine. Now, in the first orbit, for energy of an electron in the first orbit of hydrogen atom is minus 13.6 electron volts. This is the electron's energy. Now, if you want to remove that electron from hydrogen, you will have to supply 13.6 electron volts. We call this as ionization energy. Okay, of electron in the first orbit of hydrogen. That's the energy you need to supply and make the total energy zero such that the electron can be freed. Okay, so ionization energy in atoms is analogous to binding energy in nuclei. That's the energy we need to supply. What is the energy the system has? Negative of that. Okay, so if binding energy of reactants is 1800 mega electron volts, it means the energy with the reactants is minus 1800 mega electron volts. And the energy with the products is minus 2040 mega electron volts. Now you see that product energy is less than reactant energy. And what's the difference? 1800, 2040, 240. Okay. Therefore, the energy released in this reaction is 240 mega electron volts. That way. So binding energy, don't get confused and think of it as the energy which the nucleus has. No, it's the energy which the nucleus requires for its nucleons to get freed. Okay. And this energy that is released in a nuclear reaction, as I said, it appears as the kinetic energy of the products. Okay. So products get that kinetic energy, they start moving around randomly. If they collide with something, heat gets generated. So that's how nuclear energy converts to heat. Right? Nuclear energy first converts to kinetic energy, then converts to heat. Then you can convert it to any other form you would like. That is what actually happens in a nuclear reactor. Okay. They make a heavy nucleus undergo fission. Okay. Usually uranium 238. Okay. When a neutron collides with uranium 238, it disintegrates into smaller nuclei. And those smaller nuclei will be stable nuclei. Uranium 238 is unstable. Obviously, mass number 238 is unstable only, no? Greater than 170. When it breaks into smaller fragments, those fragments will be stable nuclei, means lower energy. U-238 is high energy. Products are low energy. The energy released appears as kinetic energy of the fragments. Those fragments, when they move around, they undergo collisions. That kinetic energy gets converted to heat. Okay, so that is how heat is generated in a nuclear reactor, and that heat can be converted to other forms of energy, usually electricity. Okay, so remember, nuclear reactions also obey laws of conservation of energy and momentum, linear momentum. Now, see, in this reaction, a heavy nucleus, X240, let's visualize X240 like this. It splits into two fragments, Y120 and Y120. The two fragments can be visualized like this. Let's say this is one Y20 nucleus, Y120 nucleus, and this is another Y120 nucleus. Now, these two daughter nuclei that are formed, they will have kinetic energy. Okay. In fact, the parent nucleus also might have had kinetic energy. We don't know, but you can assume it's at rest. Let's say the unstable nucleus X240 was at rest. If it splits into two fragments, those two fragments will be moving. And because the initial system was at rest, total momentum is zero, linear momentum is zero. Then the daughter nuclei which are formed, okay, or the fragments that are formed, one of them should have positive linear momentum, the other will have negative linear momentum. And because the nuclei are identical in this example, the daughter nuclei are identical, they will have to move with equal speeds. Okay, velocities will be in opposite directions, but the speeds will have to be equal because one should have positive momentum, the other should have equal amount of negative momentum because the parent nucleus was at rest. So you know how much energy was released. We just calculated 240 mega electron volts is released. And see, from the mass number, you can tell the mass of that nucleus. Okay, it is 120 atomic mass units approximately. This fragment is also approximately 120 atomic mass units. So you know the mass and you know the energy released. If you know mass and kinetic energy, you can even tell the speed of the daughter nucleus that is released. Okay, this 240 mega electron volts is the energy released in this reaction. 120 mega electron volts will be with this nucleus. The other 120 will be with this nucleus. And based on that energy and its mass, you can even tell what is the speed of that fragment. Okay, so they can ask you questions based on any of these. Just depends on how much time they want you to spend on the question. They may directly ask what is the energy released in the reaction, or they may ask what is the energy of individual fragments. They may ask what is the speed of individual fragments also. You'll have to go deeper and deeper. I mean, solve further and further. Okay, let's try another problem. Let's consider some nucleus, let's say X200, initially at rest. And for X200, let's say the binding energy per nucleon is 7.2 mega electron volts. Okay, or wait, I don't have to give an exact value also. You know this is unstable. Mass number more than 170, unstable nucleus. Let's say binding energy per nucleon is A. A is a number less than 8 mega electron volts. Okay. Disintegrates into, let's take two daughter nuclei. One of them, okay, one of them is Y50. Mass number 50 is stable. Okay, 30 to 170, they are stable. For 50, let's say the binding energy per nucleon is B. And Z150. 150 is also stable, less than 170. Let's say the binding energy per nucleon is C. Okay, so you know what is the reactant, you know what are the products. And it is told to you that X200 is initially at rest. So I want you to find out first thing, the energy released in this reaction. Answer will be in terms of A, B, and C. Okay. Energy released in this reaction. And you know the released energy will appear as the kinetic energy of the daughter nuclei. Okay. Or the new nuclei that are formed. And you know in a nuclear reaction, linear momentum is also conserved. So once you find out how much energy is released, tell me how much is the energy that Y has and how much is the energy that Z has. And once you know their individual energies, you can tell the individual speeds also. Okay, we'll get to that later. Solve this part first. I'll give you all 3 minutes. Any answers? How much is the energy released in this reaction? The energy released in a reaction generally is the energy of reactants minus energy of products. Now, energy of the reactants in a nuclear reaction, it is negative of binding energy of reactant. Okay, binding energy is the energy you need to supply. What it already has is the negative of it. Okay, so negative of binding energy of reactant minus negative of total binding energy of the products. And this can simply be remembered as binding energy of products minus binding energy of reactants. That's all. Now, what are the products here? Y50 and Z150. In Y50, the binding energy per nucleon is B and it has 50 nucleons. So the total binding energy here is 50B and here it will be 150C. And in the reactants, it is 200A. So how do you find out the Q value of the reaction or the energy released in the reaction? Binding energy of products minus binding energy of reactants. So 50B plus 100C, sorry, 150C. Minus binding energy of the reactants, 200A. That's all. That's the Q value of the reaction. That's the total energy released. Put it aside. Now, initially, the parent nucleus was at rest and it splits into two daughter nuclei. Now, those daughter nuclei must have energy. Okay, because this is an exothermic reaction, that energy released in the reaction will be with the daughter nuclei in the form of kinetic energy. So, they must be moving. System was initially at rest and it breaks into two fragments which should be moving. It means they should be moving in opposite directions with equal amount of momentum. One having positive momentum, the other having negative, such that total momentum is zero, which is the initial momentum. Okay, that means the linear momentum of y and z is equal. Okay, now you need energy of y and z. Now, so you just have to think of the relation between momentum and energy. We know that kinetic energy of a particle can be expressed as p square by 2m in terms of its linear momentum. That means kinetic energy of y to kinetic energy of z, the ratio will be mass of z divided by mass of y. Because their linear momentum is same, p square will get cancelled. It is inversely proportional to mass then. So mass of z divided by mass of y. Mass of z is 150, mass of y is 50 in atomic mass units. So this is 3:1. So whatever total kinetic energy is there, split it into 4 parts. Y gets 3 parts, Z gets 1 part of that kinetic energy. Means Y gets total 3/4 of the total and Z gets 1/4 of the total energy released. That's all. That way you can tell their individual energies. Is this clear to all of you? Any doubt in this?
No,
Okay.
sir.
Fine. Questions like this are quite common. Try another question. Very similar one actually. X240 initially at rest splits into two daughter nuclei. You just have to find ratio of kinetic energies. Do it quickly. Any answer? This is a very simple question. There are no energy calculations that you need to do at all. X240 is initially at rest. It splits into two fragments. Initially at rest means total momentum of the system is zero. Then one of them will have positive momentum, the other will have negative momentum, but the magnitude will be same. Means the linear momentum magnitude is equal. You need kinetic energy ratio, that's all. Kinetic energy is p square by 2m. So if momentum is same, kinetic energy is inversely proportional to mass. So kinetic energy of y to kinetic energy of z will simply be mass of z to mass of y. 140 by 100 or 7 by 5. Okay. So this is how you can calculate the energy released in fission reactions. When a heavy nucleus splits into smaller nuclei, you can find out how much is the energy released. Now, it's not necessary that every heavy nucleus splits exactly into two smaller nuclei. Okay. There are many different nuclear reactions possible. So they will, like, if they want you to calculate the energy released in a nuclear reaction, they'll have to give you the complete reaction and you can tell based on binding energy of reactants and binding energy of all the products, you can tell what is the energy released in that reaction. Okay. Now think about this. This is from your textbook itself. Yeah. Suppose we think of fission of Fe56. Fission means one nucleus breaking into smaller nuclei. So fission of Fe56 into two equal fragments of Al28. Okay. So one Fe56 breaks into Al28 plus another Al28. Is this energetically possible? What do we mean by being energetically possible? Anyone? Do you understand anything from that term?
Sir, I think it means will the binding energy be enough for it to react?
Binding energy being enough to react doesn't make sense. Being energetically possible means does this reaction make it more stable? Means does this reaction release energy is what they are asking. Okay. If a certain reaction or if a certain process makes a system more stable, that process will happen automatically. Okay. Otherwise, if a certain process is going to make a system unstable, then that process requires energy from an external agent. Right? So if they are asking you whether it is energetically possible or not, it means does this, I mean, does this process give more stable products or not? Think about it. I think just by looking at their mass numbers, you can tell. What is the answer? Is this exothermic or endothermic? Does this release energy or require energy? They have even given the masses of the nuclei. Okay, on the left hand side, the mass is 55.93494 atomic mass units. Right hand side, it is 2 times of 27.98191 atomic mass units. Why have they given you mass? Because mass is also another form of energy. So indirectly, they have given you energies. And you just see where the energy is more. 2 times of 27.9, how much will that be? Or 27.98191. Okay, it becomes 55.96382 atomic mass units. So there's more mass on the product side than on the reactant side. If mass is more, that means the actual energy is more, not binding energy. The actual energy itself is more. So products have more energy than the reactants. Then this reaction is an endothermic reaction. You have to supply energy for this reaction to happen. Okay, the total energy on the product side is more than the energy on the reactant side. Fine. Now, usually in a nuclear reactor, we make use of fission reactions. Mostly, uranium is what we use as the fuel. What do we mean by fuel? The nucleus from which we extract energy. That is what is fuel for us. Okay? So, usually, uranium 235 is used as the fuel. Now, what is the reaction that uranium 235 undergoes to release energy? Uranium 235 automatically does not disintegrate. Okay. But when a slow moving neutron, okay, the atomic number of a neutron is 0, mass number is 1, because there are no protons, but there is a neutron. So proton number is 0, protons plus neutrons number is 1. So we represent neutrons like this, 0 and 1. When a slow moving neutron collides with uranium 235, what happens is the uranium 235 absorbs that neutron. Then what does it change into? It changes to uranium 236. This undergoes a spontaneous disintegration process, and it can disintegrate in multiple ways, not a single way. Okay, I mean, there are multiple reactions through which it can disintegrate. Okay, let me just give you the equations of those reactions. You don't have to memorize these. Just a moment. Yes, when uranium 235 absorbs a neutron, these are the three different reactions by which it can disintegrate. Okay, in all of them, you see there is a uranium 235 absorbing a neutron and converting into uranium 236. Okay, in the third one, it's not there. I think they missed it. It should be there. Then it breaks down into smaller fragments. In one reaction, it forms Ba144 Kr89 and releases 3 neutrons. In another reaction, it gives rise to Sb, stbium 133. What is Nb? What does Nb stand for? I think niobium. Find out. But if it disintegrates through that reaction, it produces 4 new neutrons. Okay. And if it disintegrates according to the last equation, it produces 2 new neutrons. So you can see that for every 1 neutron that uranium 235 absorbs, it produces multiple neutrons. And these neutrons which are produced, these new neutrons which are produced in the reaction, can further go and collide with other uranium 235 nuclei and keep the reaction happening. So they can participate in a chain reaction. Okay. See, to initiate any of these reactions, we need a neutron. Fine. Suppose you give one neutron. Okay, there are many nuclei of uranium 235. You introduce one neutron into that. It will be absorbed by one uranium 235 nucleus. Reaction happens, multiple neutrons will be produced. Those new neutrons will go and collide with the other uranium 235 that are present, and the reaction will go on like that. So this chain reaction is what nuclear reactors are based on. Fine. And if you have patience, you can even calculate how much energy is released in each of these steps. Like you find out from that binding energy curve, you can tell what is the binding energy of uranium 236. And you can tell what is the binding energy of these. Fine. Ba144, Kr89. If you know binding energies of reactants and products, you can tell how much is the energy released in the reaction. Okay. So whichever way it disintegrates, you can see uranium 235 is an unstable nucleus. The products here, okay, mass number 144, less than 170, it's in that 30-170 range. 89 is in that 30-170 range. All these are in that 30-170 range. So they are all stable products. So unstable reactants forming stable products means energy is released in all these reactions. So whichever path uranium 235 disintegrates along, it is going to release energy. Okay. So suppose there is a certain amount of mass of uranium 235 in a nuclear reactor and you introduce some neutrons into it. The reaction will get started and the reaction will continue till all the uranium 235 is exhausted. Why? Because after every step of the reaction, new neutrons are formed. They will go and collide with other uranium nuclei and the reaction will continue. Okay. But there is a problem. In fact, there are multiple problems. These new neutrons that are produced, okay, these are high energy neutrons. High energy neutrons cannot be part of this reaction. They won't be absorbed by uranium 235. Only low energy neutrons, means slow moving neutrons, can be absorbed by uranium 235. Okay. So this chain reaction cannot go on unless you slow down the neutrons which are formed in the reaction. Fine. And how to slow down these neutrons which are formed? Neutron is a very, very small particle, no? In fact, it is much, much smaller than an atom. So these neutrons, fast moving neutrons, they can easily escape from the nuclear reactor. Even a wall cannot prevent a neutron from escaping because wall is made of what? Atoms, molecules, atoms. But most of the space in an atom is empty. Neutron can pass through that space. Fine. So you will need very thick walls and you will need material, lot of material to stop a neutron. What are the chances that a neutron collides with something? Very less chances, no? Because most of the space in an atom is empty. When a neutron wants to pass through an atom, it can freely pass. Okay. But if there are many atoms that it has to pass through, then there is a chance that it undergoes a collision somewhere and slows down. Okay. So these neutrons which form or which are the products of these reactions are high energy neutrons. They cannot participate in the next step of the reaction. They cannot go and get absorbed by another uranium 235. But we want the reaction to go on. We want the nuclear reactor to continue giving us energy until all the uranium is exhausted. Okay, we don't want the reaction to stop. Okay, so what we do, we intentionally slow down these neutrons. To slow down these neutrons, something called a moderator is used. Okay, usually the moderator used is heavy water, D2O. Okay, the entire nuclear reactor will be filled with heavy water. I mean, all the empty space in the nuclear reactor will be filled with heavy water such that these fast moving neutrons collide with it and slow down and they will be able to participate in the next step of the reaction. Okay. So that is how we overcome this problem of high energy neutrons. We can make them low energy neutrons. But when these fast moving neutrons slow down, they will release a lot of heat. Of course, that heat is what we want from the nuclear reactor, but we don't want it to be too high also. We don't want too much heat to be released. So in a nuclear reactor, there is something called a coolant used. Okay, coolant keeps circulating in the nuclear reactor, absorbing the heat or removing excess heat from it. Okay, so the name itself is self-explanatory. You need a coolant to keep the temperature under control. There's one more problem. For every one neutron absorbed in any of these reactions, there are multiple neutrons produced. Okay. Suppose uranium follows this path of disintegration. Okay. Now, if you introduce X number of neutrons into the nuclear reactor to start the reactions, you introduce X number of neutrons. After one step of the reaction, 3x number of neutrons will be present. Then after another step of the reaction, 3 into 3, 9x number of neutrons will be present. Then the next step, 9 into 3, 27x neutrons will be present. They will collide with 27 uranium nuclei, 27x uranium nuclei, and so on. So in the first step, X number of uranium-235 nuclei will disintegrate. In the next step, 3x number of uranium-235 will disintegrate. In the next step, 9x number of uranium-235 will disintegrate. So the number of nuclei disintegrating step by step increases exponentially. And whenever uranium disintegrates, it produces energy. That means if you allow this reaction to go on without any control, the energy released in the nuclear reactor will increase exponentially, which is a bad thing because nuclear reactions release too much energy. Okay. See, we want a lot of energy to be released. Yes. But we don't want it to go out of our control. If you allow this chain reaction to continue, it will go out of our control. So what we need to do is these neutrons that are produced in the reaction, fine, we need to somehow remove some of them. We don't want all these daughter neutrons to participate in the next step of the chain reaction. We want only some of them to participate. So we need something, or we need a mechanism by which we remove these neutrons. And for that, we use something called control rods. Okay, control rods are usually made of cadmium. Cadmium is a material which has a very high tendency of absorbing neutrons. Okay, so whenever you think the reaction is going too fast, okay, or energy is getting produced very rapidly, okay, control rods are introduced into the nuclear reactor. They will absorb the free neutrons. They will decrease the rate of reaction. They will decrease the number of nuclei participating in a reaction step by step. Okay, so the heat released can be brought under control. Usually, you can see for every one neutron absorbed, there are multiple neutrons produced. Now, which of these reactions uranium undergoes is not under our control. Any of these can happen. And usually it is found that for every one neutron consumed, okay, for every one neutron consumed, on average, 2.5 new neutrons are produced. Okay, see, sometimes 3 are produced, sometimes 4 are produced, sometimes 2 are produced, but on average, 2.5 new neutrons are produced. Okay. Now, if you allow this multiplication to continue, 1x produces 2.5x. Next, 2.5 into 2.5 becomes 6.25x, and so on. This will lead to an exponential rise in the energy being released. We don't want that. We want a linear, or we want a stable production of energy. So what we do is we try to keep this multiplication factor close to 1. Okay. This factor, the factor by which the number of neutrons gets multiplied in each step, is called the K factor or the multiplication factor. If K factor is greater than 1, it leads to exponential rise in the production of energy. Okay. If K factor is less than 1, means for every one neutron consumed, less than one neutrons are produced. Then what will happen? It will slow down the rate of production of energy. Leads to decrease and eventually switches off the reaction or the reactor, you can say. So we need to keep K close to 1. So what will happen? They introduce a few neutrons, they allow the reaction to happen. When K is becoming too high, they introduce control rods. They remove some free neutrons. They make K less than 1. If K is less than 1, reaction will slow down. Okay, when it becomes too slow, remove the control rods. Multiplication will increase. When too many neutrons are produced, introduce control rods. When too less neutrons are produced, remove the control rods. That is how they maintain stable production of energy in a nuclear reactor. So control rods are very important. Without that, it will lead to blast in a nuclear reactor. Exponential rise in the production of energy will lead to a blast of the nuclear reactor. That is what control rods are used for. And see, these daughter nuclei that are produced, whether it is barium, krypton, Sb, Nb, Sr, whatever it is, strontium, any of them, they are all freshly produced nuclei. Okay, when the reaction happens, these nuclei are produced. Usually, not just in these reactions, in any nuclear reaction, the daughter nuclei are highly unstable. Now, how can I say they are unstable? They are all in that stable range 30 to 170. Why am I saying they are unstable? See, even though they are in that range 30 to 170, fine, you can say, like, see, usually atom is a stable entity, right? It has protons, neutrons, electrons, it is stable. But in atoms also, there are high energy atoms, low energy atoms. You know that in hydrogen, electron can be in different levels of energies. A hydrogen atom itself can go from high energy state to low energy state. It doesn't have to react with something. Fine. Usually chemicals, why do they react? To attain stability. But an atom itself, just by demoting its electrons from higher orbits to lower orbits, it can release some of its energy. Okay, we are talking about that kind of instability. So the daughter nuclei of a nuclear reaction are usually highly unstable. How they attain stability is they emit radiation. Okay. Usually hydrogen atom also does that only, no? When an electron is in a higher orbit, it jumps to a lower orbit by releasing a photon. Fine. Lyman series, Balmer series, we had discussed that. Same thing happens with nuclei also. Unstable nuclei can attain stability by emitting radiation. This radiation is usually in the form of gamma rays, which are harmful to us. Okay. That is why we should never expose ourselves directly to a radioactive material. Radioactive material means unstable nuclei, material having unstable nuclei. They will usually be emitting gamma radiations, which is unsafe. When gamma radiations are incident on our skin, our DNA will get damaged. It will cause cancer. Okay, that is the problem with UV rays. So, in a nuclear reactor, obviously there are a lot of unstable nuclei being produced. They will be emitting gamma radiation. We don't want that radiation to leak out of the reactor. So for that, it is very important to shield the nuclear reactor. Okay. Shielding of a nuclear reactor prevents harmful gamma rays from escaping the nuclear reactor. Right. So basically, these are some terms that you need to remember. First thing is fuel. Uranium 235 itself is the fuel because that is what provides the energy for us. Then moderator, what are moderators used for? They are used to slow down the fast moving neutrons. Next, coolant, obviously to keep the temperature in control. What are control rods used for? When the rate of reaction is going too high beyond control, or when the rate of production of energy is going beyond control, introduce control rods such that some free neutrons are absorbed and the rate of production of energy decreases and comes under control. When the rate of production of energy becomes too low, remove the control rods. Then the rate will increase again, tend to increase again. So you need to keep inserting control rods and removing them to maintain a stable rate of production of energy. And finally, shielding. You know what shielding is needed for. Okay. Let us also briefly discuss. See, as of now, radioactivity is not there in syllabus for NEET or JEE mains. Okay. JEE advanced, it is definitely there. So we will discuss this at a later time, but just understand what radioactivity is. Basically, an unstable nucleus undergoing a process where it attains stability. That is what we call radioactivity. Okay. Now, what are the different ways in which an unstable nucleus can move towards stability? First is something called an alpha decay. Basically, what happens? A nucleus, usually a heavy nucleus. What is the problem with heavy nucleus? It has very high mass number. It has to reduce the mass number. So a heavy nucleus, what it does is it releases an alpha particle. What is an alpha particle? 2He4, two protons, two neutrons will be gone. If two protons, two neutrons are gone, let's say the heavy nucleus is ZXA. If two protons and two neutrons are gone, then it will be left with Z minus 2 protons. And because the number of protons has changed, atomic number changes, element changes. And the mass number decreases by 4. So heavy nucleus, if it is able to decrease its mass number, means it is moving towards stability. So this is one process by which some nuclei tend to attain stability. So if a nucleus emits an alpha particle, its mass number decreases, okay, and it moves towards stability. Next, there is something called beta decay. In beta, there are two types. One is beta minus decay, and the other is beta plus. In beta minus, what happens? These are interesting processes actually, more interesting processes. In beta minus decay, a neutron, okay, decays. We think that neutron is a fundamental particle, but neutron can break down into fragments also. Okay, a neutron decays into a proton. Proton symbol is 1p1 and an electron. Okay, because total charge of a neutron is zero, no? So if it is producing something which has a positive charge, it should also produce something which has a negative charge. It produces a proton, an electron, and a new particle called an antineutrino. You don't need to know much details about this, just remember the name. This is what happens in a beta minus decay. A neutron disintegrates into proton, electron, and antineutrino. Now, this electron and antineutrino, they go out of the nucleus. They are expelled. The proton that is produced, it stays inside the nucleus only. It doesn't go out. So, suppose there is a nucleus ZXA which undergoes a beta minus decay. What is happening? One neutron is lost, but one proton is produced. If a proton is produced, atomic number changes. Okay, that means the element symbol changes. One neutron is lost, one proton is produced, means the total number of nucleons is the same. So the mass number remains the same. Okay, the newly created proton, it stays inside the nucleus only, it doesn't go out. Okay, so atomic number increases, mass number stays the same. And along with that, an electron and an antineutrino are produced. Obviously, some energy will be released. This is what happens in a beta minus decay. Next is beta plus decay. In beta plus, what happens? A proton converts into a neutron. The proton is positively charged, neutron is neutral. Then where will the positive charge go? It releases a particle called a positron. Okay, positron is another fundamental particle. It has the mass of an electron but the charge of a proton. Okay, so positron and something called a neutrino. Okay, this positron and neutrino, they are expelled out of the nucleus. The neutron that is formed stays inside the nucleus. So you can write the nuclear reaction also. If a nucleus ZXA undergoes a beta plus decay, proton converts to neutron, means proton number decreases. So Z minus 1. And if proton number is changing, atomic number changes, element symbol changes. Proton converts to neutron and stays inside the nucleus, no? So mass number doesn't change. One less proton, but one more neutron. So mass number remains the same. Plus positron plus neutrino plus some energy, of course. So this is another way in which some nuclei attain stability. And then finally, there is another way of attaining stability that is called gamma decay. Now, in gamma decay, there are no fragments or particles which are released by the nuclei. Just a high energy nucleus converts to a low energy nucleus by releasing energy in the form of radiation. Okay. So, energy is released in the form of gamma radiation. So these are the many different ways in which nuclei can attain stability. Okay, and this is what we call radioactivity, some process by which nucleus attains stability. Okay, fine. A little bit is left in this chapter. Nuclear fusion. Okay, thermonuclear fusion, how to make it happen, what happens in stars, that is there. We'll discuss that in the next class, and next class itself we'll start uh, semiconductor devices also. But make sure you practice problems. These chapters, dual nature, atoms, nuclei, semiconductors, these are very small chapters and you will definitely have questions from them. Okay. So these are very, I mean, highly scoring chapters. Very few concepts are involved and questions will be asked based on those concepts only. So it's very easy to score. But you should make sure that you practice sufficiently enough that you solve these questions quickly and correctly. Okay. Thank you all. We'll continue in the next class.